But today he's going to talk about the charm production in the UPC and LHC, which will have a common interest from RC group here. Please.
Okay, thank you very much. Thank you, for the hospitality, and it's great to be here. And I'm looking forward to interacting with the group. I'm here until Friday, including Friday. So, and I hope to get the feedback on this topic, and I will talk about the inclusive charm photoproduction in ultraperipheral collisions at the LHC. So, well, first some brief motivation why UPCs are interesting, and they are very good probes of nuclear structure. And then I will sort of briefly describe the what we call the generalized photon-nucleus FONLL approach for UPCs. So we took the FONLL approach developed by Frixione, Cacciari-Nason some years ago, and then we adapted it for UPCs. So I will sort of go over how one calculates the open charm production cross-section, and then what are the ingredients, fragmentation functions, and then I will spend some time on this electromagnetic dissociation and the photon flux, which is for the nuclear case. And then I will benchmark this with the HERA data. So I want to see how, well, whether the old Fortran code didn't sort of, well, how the data are described. And then using these parameters, I will add on to the specifics for the UPC and do the predictions with for D0 production and comparison with CMS data. So this work was really sort of sparked by Gian Michele Innocenti, who is at CMS and he's doing the measurement. So he kind of motivated to do this calculation, and then Matteo Cacciari, who was one of the authors of FONLL, he kind of recently joined us and hope to get some input from him. So let's start from the UPCs. We are looking at UPC collisions. So ultraperipheral collisions, large impact parameter, larger than 2 radii of these nuclei, such that the hadronic component is suppressed and electromagnetic component is enhanced, so at least one of the nucleus emits a photon. This is much cleaner environment than standard AA collisions, and in these collisions we are looking at the photon flux is calculated using the standard equivalent photon approximation, and it is enhanced by z-square of the nucleus. These are the conditions for the LHC, so we are looking for lead-lead into lead-lead collisions at square root of s 5.36. So there are many experts on the UPCs here. These are great reactions if there is hard scale present, because then we can use perturbative methods. Here are 2 examples. One is dye-jet photoproduction, and this very interesting paper by Atlas on dye-jet photoproduction. Is there a way to maybe close this, because I'm getting so much reflection that oh yeah, that's better. Okay. Then I don't see anything here. So when I try to point here, thank you. So dye-jet photoproduction has this direct component, and oh yeah, has the this direct component and the result component where the photon results before interacting and produces 2 jets. And this is Atlas measurement, triple differential cross-section as a function of XA in beams of Z gamma and different sums of transverse momenta. The other example is, of course, our favorite J-psi exclusive diffractive production, where we produce the J-psi rapidity gap. And there has been a lot of measurements on both sides on the experiment, a lot of theoretical calculations. You see the spread of these calculations. That's a very amusing plot. So here you see the rapidity distribution at CMS and LHCb, and then the energy dependence. So we hope to learn something about the nature of the pomeron from this production. Now, these are all excellent proofs of nuclear structure, but they have their own features. So the dijet photoproduction, because it's a dijet, you need the high transverse momenta, so it's moderate X. So if I go back to this slide, of course, this X, well, this is the range of X, right? Sort of moderate to largish. And then the vector meson exclusive production goes to low scales, but it's exclusive and diffractive. You need to model the wave function. And it's kind of complicated. It doesn't really measure the inclusive gluon density, but the pomeron. So you might wonder whether you need the GPD or dipole thing. So it provides a different information. So we are looking in here in this talk. I'm going to look at open charm for the production. So we are looking at D0, maybe D star in the case of HERA. This is photoproduction. So, but here we have a charm mass and we have a scale, and it's inclusive, so the nucleus breaks up. And so hopefully the factorization and universality of PDFs works. And there have been in the past calculations, including Spencer and collaborators on this process. A little bit more about the kinematic space, including an obligatory plot of every small X physicist. So in nuclear DIS, so far, the DIS probe, this X and Q square, these are all fixed target data. So kind of moderate to large X. We hope the EIC can go to lower X. So this is a plot that I took from this nice paper where they, so these squares, colorful squares, indicate the simulated data for different EIC energies. So you see how it kind of enlarges the phase space towards the lower X. Now, meanwhile, we can do charm photoproduction in UPCs because the charm then is produced mainly in gamma glue fusion. So one tests the nuclear gluon density. And of course, we can test these different scenarios. Do we have DGLAP, DFKL, and whether we enter or not the saturation. I am going to stick with standard collinear factorization with nuclear modifications. So I'm not doing a small X physics, but I can show you some predictions on that.
Question from the non-expert. I mean, where is this large Q squared coming from? The photon itself cannot have a large transverse momentum.
No, so it's a mass and PT here.
Okay.
Yeah. So that's PT
of
the D meson.
So it's the energy which goes in, which can be large. The longitudinal momentum of the photon can be large, right?
Or small or large.
Yeah, but I mean, well, the Broad's contraction gives you a large longitudinal momentum.
Yeah,
right?
yeah, but then you have the, I mean, the fraction of the photon the energy of the photon. This is longitudinal, but this is the transverse scale gives you the scale, right? So then you have, so this acts like your Q square of your,
okay,
right?
Okay, all right, thank you.
H1, so these are very nice. This is actually a paper from '98 where they measured the D star at H1. And I will show the data on the cross section, but what additionally they did, they have some method which I do not entirely penetrate, where they actually extract the gluon density themselves, which is very nice. So you can see in their method the data points, and here, for example, the stars are this photoproduction gluon density from photoproduction extracted from the data compared to the fits. These are old data. So this is very, very nice process. Yeah.
on the left, the x-axis is labeled u squared. Is that q squared?
Yeah, it's sort of, well, they of course have to have some theory, so they have some next to leading order calculation, and then they evaluate this q square, this mu square from this NLO calculation. It's a quite involved procedure. This is why I'm saying I don't quite understand it, but I think it's worth looking at. In the nuclei, we tried to make some estimate of the kinematics where you are in x and q square. This is really crude and probably too maybe even too low. Like if you assume this sort of roughly relation and your quarks somewhere going in the same forward rapidity region, this is more or less what you get for PT between 0 and 12 and rapidities between minus 2.4 and 2.4. Of course, this is charm level estimate. Fragmentation shifts the estimates to higher q square. So this is very crude, but it gives you some idea where it sits with respect to the DIS nuclear data. Yeah.
So this is based on you're seeing only the D0.
Yeah, so this is
what do you
just
assume about the D bar?
Yeah, so here, this is why I'm saying this is very crude. What I would like to do is really do some deconvolution about, use the mapping of the calculation to the kinematics. So we spent quite a bit discussing, what is, we are not really assuming much about the other quarks. So it's not very precise. Now, going more into
one more question. Maybe this is a kind of experiment question too. So how you determine which photon, which nuclei?
I will go into that a little bit. It's this ZDC.
Okay.
Yeah.
Okay. Then you can.
Yeah.
You can
and
ambiguously.
they put some conditions. I'll show you something. So we are using this FONLL. This was developed by Cacciari-Frixione-Nason for heavy flavor photoproduction and hydroproduction. And so Cacciari developed a code for this. So what is the content of that? So this framework connects small transverse momenta with high transverse momentum region. And essentially at small transverse there are mass effects, and then there are logarithmically enhanced terms log pt over m. So it's accurate up to next leading order, and then it includes these logarithms. And both direct and resolved contributions are included. However, one should mention that once one goes beyond leading order, they are related. So only some is observable. And in fact, a large part of the work is to make sure how you treat certain contributions, which in some sense occur both in one and in the other. So schematically, the result formula looks like that. This is called FONLL, fixed order plus next leading order logarithm. You have fixed order, which is fixed order result with masses up to this order. Then there is a result with logarithmically enhanced terms like these, and neglects the terms which are suppressed by power of m. So mass only sits here. Then there is a subtraction of the massless limit of the fixed order. So all terms suppressed by power of m dropped, but logarithms are retained, so they cancel here. So this is kind of a truncated resum, the result. And then there is some damping function, which is regular at PT, and then it approaches unity at large PT. So this is their
so
framework.
The result is like, I remember at some stage you also have to introduce the fragmentation. Right.
Yeah, so this is like because these logs are so there are different emissions from different lines. So
Okay.
so the ones from finite state is essentially
Fragmentation.
Yeah.
Okay.
So this M is a T0 mass?
Sorry.
This M is a T0
Well,
mass?
here M would be this is on the level of the charm quark.
Jump on.
Yeah. Okay, so now we go, now we have that, now we fragment, okay? So there is a convolution with the fragmentation function, and here there are options. I mean, one option is Peterson. I mean, it's nice because it's this nice compact formula. I'm gonna use the parameter choice that was used in the original Frixione-Nason for the D star. For the D0, I also use the D star. I also use the Peterson, but I mainly use this BCFY fragmentation function. And in these works, they put like a two-component model because the D0, a lot of decays come from D star, but there are also direct kind of transitions. So we use mainly this, mainly with this parameter choice.
So that Yuan is different Yuan. Okay, it's not me.
Yes. It is indeed. Okay, now there are a number of differences between the EP and UPC AA. So of course there are different fluxes, and I will talk about them in a moment. Now, in some data sets in EP, they say it's photoproduction, but then in two data sets, they have Q squared like 1 or 2 GV squared. Then at HERA, they can do the beams in this photon energy. I wonder to what extent one could do this in UPCs. We integrated over, of course. And then we have a proton versus nuclear target, so there's nuclear modification. Now, for the photon fluxes, this is just a basic, of course, it's very well known. So this is the electron, so this is the photon flux from electrons. And this is this formula plus some corrections. There is a nice discussion in this paper about different type of cuts, but basically this is a electron to photon splitting function in the log, and so it's this formula. And then for the nucleus is of course the standard point. Well, this is the point like flux that we take. And one thing to note, which is kind of what at least personally struck me, was that that at HERA this range for D star is here. So it extends to very large photon photon energies, where essentially this nuclear flux is whereas the nuclear flux is dropping because of these explanations. So that's just
But here Z is the energy fraction, photon
exactly
energy over
fraction.
ion. But the ion energies are higher.
Of course. So yeah, so but then overall, right? It means that the LHC is not that. I mean, it is higher in energy than HERA, but because of that effect, you have a little bit of.
I mean, look at this as a log scale index.
So yeah.
So it's a 2 order of magnitude.
Z squared. For nucleus, you have square times by Z squared, a large number.
So
You have nucleus.
But
yeah,
that's an
exactly.
overall factor.
That's this factor here.
So they are trying to look at energy fraction carried by photon.
Yeah.
That's,
So that's okay. So now some of the questions. How do they do this? So in CMS for this, they look at what they call the 0n xn. So 0 neutrons in one ZDC and at least 1 neutron in the opposite ZDC. Okay. And then on top of this, they require some extra rapidity gap on this side to suppress some hadronic interactions. So after scattering, you have this situation, 0 and xn. So now there are two problems here, because one is that, this is unbroken, but it still can be broken if there are additional interactions. So one needs to account for this survival probability due to electromagnetic dissociation, some soft interactions. And then the other thing is that this means that, some coherent diffraction is rejected. In EP, it is included, and theoretical calculation is included.
Yes.
So we have not subtracted it. We did, from asking Mark about the number, Mark says it's 10%. But we have to calculate it, how much it is. Some estimate that they provided us are of this order. So
that's like consistent with HERA that defect events is about 10%.
Well, yeah, but this is just
I mean, this is a nucleus.
coherent, the nucleus. So this has to be looked at in. We have to look at it more carefully. What is going on? But one has to include this electromagnetic dissociation. So this means this photon emitting nucleus is left up unbroken if you take this requirement. So this survival probability is essentially one assumes this factorization of the hard and soft excitation probability, and one can end up with calculate this effective photon flux, where you fold this photon flux with this survival probability, and it's given by, well, I didn't write the formula, but you can find it in Spencer's paper, and it's essentially the probability of no excitation, and they have very nice paper here where they deal with this, and they calculated this effective photon flux, and then you can divide by the photon flux that I showed you before as a function of the photon energy, and you get this curve. Okay. Now, what we did was, in principle, I could take now this flux and run through all the calculations. I would say for historical reasons and the evolution of our understanding, what we do is actually do the bin by bin correction after. So I do the calculation with one set of parameters. I calculate this ratio for the D0 in PT and Y, and I do the correction. Now, that's, at the moment, we've done a lot of runs with, changing other parameters, but this should be good enough for now. It's, you see, the higher PT, the larger this suppression down to 0.4, and also at larger Y, because this is where the photon, So it's a large effect.
So what do you mean by unbroken? That I don't lose a nucleon? Am I allowed to excite the nucleus? There's lots of very soft excitation. I'm scrapping myself. Do I lose coherence if I go to the
I don't know if I'm the best person to answer. It's it's a question of what the ZDC measures or doesn't measure, right?
Yeah, but what's the physics? What do I require for this to work? That I really go really elastic, or am I allowed to do whatever? What may be excitation, which of course are accidents in the nucleus, right?
There's a lot of discussion about that, more in the context of EIC separating coherent and incoherent production, and there's this whole mystery because if you look at things from, say, a shell model structure, lead and gold are very different.
Absolutely.
And so that would tell you that they should behave very differently. On the other hand, if you look at them in a hadronic high energy picture, they're both Wood-Saxon distributions. You expect the same shadowing. And so that would tell you, if you're dealing with high energy reactions, they should be very similar. And as far as I know, there is no resolution to that problem.
Okay, so I joined the club. Okay, okay. So my confusion, I'm not the only one. Correct?
No, you are not the only one. And once you start thinking about it, then you go very deep into the rabbit hole.
Spencer can correct me, but from what Spencer educated me many years ago, that some of the excited contribution actually has been included in nucleus, right? So in the sense that although you have photon, the Coulomb interaction could exact your nucleus.
Of course. I mean,
Yeah, that's
how
if you were talking about exchanging an additional photon,
Yeah,
which that was in this P of B I heard last
right.
slide.
I think that's what he was
Yeah.
asking.
No, but you send this
But
photon.
there's also,
You have a photon going out from your unbroken nucleus, right? And the unbroken nucleus can come out in an excited state, right? Coulomb excitation.
Yeah, that's it.
Right.
That's
And so
that Spencer told me many years ago. That has been included. So in the sense that also contribute to the Z score, right? Is that right?
I mean, I think you're talking a different thing. One is you have a single photon, which is what I think where you have a single photon, it produced the CC bar.
right.
The question is, what else does it do to the nucleus? Because you can have that CC bar, maybe it doesn't break up the nucleus, or maybe it breaks it up but only emits a proton, or excites it or something in ways that would not trigger a CDC.
Okay, anyway, I think we should
Yeah.
not distract too much.
Okay, let me go and show you the comparison with the HERA data, because that's interesting in itself. I have to get to LHC. So we reproduce the results by Frixione-Nason with updated PDFs. So this is these are type of PDFs that we tried, the different photon PDFs. This is another story, the parton in the photon. We use some older things, and this has to be looked at. And then we use the Peterson function. And then there are these 4 data sets from HERA. These are older data from H1 Zeus and H1 2012. This is the Q-square cut. And this is the energy range. Usually this is denoted in DIS by Y, but since Y is rapidity, I used Z. So anyhow. So this is the calculation. And these are EP cross-section, not gamma P, EP cross-section. And you see this H1 33, 44, Zeus 2012 H1. And then you have bands or renormalization scale dependence. And there are actually 2 calculations. There is blue, which is supposed to be superior, which is FONLL, and then fixed order massive, which is this gray. And you kind of see that
I see.
that there is, like here you can still see, but there is, it seems like the superior calculation has a little bit too soft of a spectrum in PT. And this is something to be still, understood why it is that. Because there is that.
Suppose you have resummation there, so you should be bigger than
it's actually softer. It acts like a fragmentation a little bit. Right?
I see.
So this is how it does. And here I'm using also Peterson function, and I'm using 2 different values for the resummed and fixed order from some papers they were using. This effect, this gray is a little bit already suppressed. So anyhow, this is how it looks like in PT. Maybe I skip that one. One thing is, which will come later, is if you play with charm mass, in FONLL, you get, if you put a heavier charm mass, it suppresses you at small PT, but then it moves you at high PT. So this is the one of the things. And then here also you see, or you don't see, the difference between the magenta and the black curve. These are 2 different photon PDFs, and they are identical almost. Okay.
Maybe
Now,
can I ask just
yeah.
a naive question? Maybe go back 2 slides, I think. Sure. Yeah. Any of these will be fine. So you have the fixed order results. You also have sort of this sort of mixed scheme of fixed order plus next leading log. What if you, like, if you just included next leading log result, presumably, I mean, you have access to this, right? Does that improve?
Yeah, so, well, okay, so I didn't try that, right? You mean truncated parts of the logs?
Yeah, essentially
Yeah.
just an RG improved calculation.
Yeah, so I didn't try to truncate. So this is just this would be just a fixed order, like this first term that they had, and then this would be just all these logs. So no, I don't have anything in between. So I'm not sure. Quickly, the rapidity distributions. This is for in beans of PT, low PT bean 3 to 5. 5 to 10, and then this is a different energy. So, you know, this you see the quality of the data and the shapes, you know, it sort of roughly agrees. By the way, here, proton is going into the positive rapidity region. Same thing with Zeus, so more or less consistent here at high PT, you start to see the same effect. And that's similar for the H1 data, different PT beans. This is the highest, this is the lowest. I mean, the shape agrees, but the normalization here is. Okay, so now the main thing, this, so what does it, we now put that, so we have benchmarked this at HERA, and now we take the flux for the nucleus of the photons with the EMD correction. We put the nuclear PDFs, we play a little bit with the charm mass, and then we put the fragmentation function, this BCFY. Also, I compared with the Peterson just to have some connection with HERA, and then again I run with these two different scenarios. So now the CMS, just to confuse, like the photon now is going to the right. But I didn't want to change the HERA, because then HERA people will say, well, but we had proton going into the positive direction. These are so this is rapidity distribution. This is 2 to 5 PT, 5 to 8 GV, 8 to 12. These are beans of CMS, and then I will show you the very recent slides. They also have very preliminary data. I have 2 slides on that. These are the parameters, and the inner parts, so the big blue band is the renormalization plus factorization scale dependence. The inner band is the PDF uncertainty. This is FONLL, and now gray is the fixed order. So the data seem to be now consistent.
Fixed order, okay.
More or less, with the calculation.
So you use the EPPS.
I use EPPS, so now I can show you. Okay, so now a few variations. So this EPPS, the blue one is again the EPP, everything here is EPPS, but now I change the mass. Now I use the 1.3 because the EPPS is evaluated, well, is extracted with 1.3, so that's the consistent mass. But then I can ask the question, well, what happens if I change this mass a little bit? And then you get into this magenta. So these darker shades are PDF uncertainties, and then I put here lines because if I were to put too many of them, you wouldn't see anything. So you see again that the lower PT, the higher mass is of course lower, and then at higher PT it is higher because there is less resummation. So it seems like, so you see the same pattern as at HERA, and it sort of seems that, I mean, everything within the errors is consistent. The data like this higher mass a bit more, but you know, you cannot make any conclusions. It's just to illustrate, you know, how things vary.
The uncertainties of the data, sorry, they have the black boxes.
Yeah, the black boxes here, here, and here, right?
Oh, but this also depends on nuclear PDF, right? So
yeah, of course, I will show you.
So do you assume that then
each time you have your reaction, the nucleus automatically breaks up and you get a signal in the CDC, or do you account for
well, you would have to.
non-CDC breakdown?
I will. This is the question to John McKellen, right? Because I'm not making the measurement, right?
I mean in the calculation.
Well, in the calculation, I'm doing the same calculations that at HERA, but then the EMD takes care of this fact that I have the suppression of the flux and an unbroken nucleus. On the other side, I am not making anything there because any assumption. So here I would have to, if the diffraction is 10%, this all goes, the calculation goes down.
Go down. Wait a second.
Because I have to subtract.
Oh, yeah, that's true.
But I don't know, then you have to do the full simulation. I don't have subtracted diffraction here. So it's, so if it's 10%, then you have to move it by 10%. But
I see.
you have to do additional calculation with the diffraction and somehow.
Or maybe in other words, your shadowing is maybe overshadow or something.
Yeah.
Right.
Right.
Yeah.
This is a different PDF. This is NNPDF. Now NNPDF comes with a charm mass 1.5. And it's very consistent with the EPPS 1.5. So you have the same behavior, okay? Similar description. Now you can ask, well, what happens if you don't have nuclear PDF? Is you have proton PDF. So this is proton PDF. So here it's CT18. NLO, because this is the proton baseline for the EPPS, okay? And then now I show you just the comparison here. And then here also different masses variations. So the red one is 1.5 and the orange one is 1.3, right? So what you see is that in the highest PT bin is a very little effect. And here you start see nuclear effects because this calculation is higher. If you look at especially at these inner bands are higher than these. Okay. So here you start seeing shadowing. It's 25%. Here you see, if you kind of look very closely at the central values, you see some 5% or something like that. So. Now, here, okay, we didn't play too much with the D0, with the different fragmentation functions, but I have just one plot to show for consistency. So this was shown before with BCFY, but I also used the Peterson. So here, this band is just to be compared with this band. So the only difference between this light blue and this light blue is this different fragmentation function, and it seems to be consistent between the calculation. However, what I also did here, because this is Peterson, I also put here this fixed order, and these parameters are exactly the same as for D star for HERA. Of course, the fragmentation fraction is different, but the functions are similar shape, just to see where the fixed order lands, and it's brought down because this parameter makes it a little bit softer. Still, these data are between the FONLL and the fixed order. But maybe if we put in, then again, diffraction, things will change a little bit. So here, this is how the PT distribution look like for different PDFs in bins of rapidity. So this is rapidity -2 to 1, -1 to 0, 0 to 1, 1 to 2. And then you see how the uncertainties blow up at lowest PT beam, right? This is also lowest PT beam 0 to 1. So you start to be, end up. But if you can have a measurement there, that would be great, right? Sure. Because you can have a lot of mileage in terms of constraining these. Okay, so just to see what is happening, if you look at these PT bins that CMS has 2, 5, 5, 8, 8, 12, and then you kind of take the middle of this bin and plot the ratio for EPBS. This is how they look, right? So you get, here you get this 25, 30% reduction, 20% and less. I mean, it depends, also where you are. For the highest PT beam, I think, the measurement's somewhere here. So it's all, just gives you, consistency how things look like. And now I will show, before that, we looked at a wider range of rapidity, -4 to 4, 2 to 3, 6 to 7, to see how big is the cross section. Of course, here it gets killed by the flux, but I don't know. Maybe one can still measure something at 2.5 somewhere. Here, of course, one is testing more the photon structure function, if you wish. And so there is some dependence that comes up on the photon parton distribution. So that's interesting in itself. Okay, so here I have 2 slides that Gian Michele prepared with what they have now, the more preliminary data, because they have now, in this bin 2 to 5, they now have a split in rapidity. So they see the rapidity slope. Now there is also the CGC calculation. This is this line. And here there is a ratio of, essentially, a ratio of data to the proton prediction from FONLL, and also the FONLL prediction for the nucleus versus the proton. And they sit here, whereas the data starts to go more down towards lower X. And this is how you look, how it looks like. So this is essentially, the same type of plot that I was showing before. It's much nicer because it wasn't done by me, it's by CMS. But the calculations are all what you saw. So now these are the data for this lowest bin as a function of rapidity. And now you see here from left to right. So the 2 leftmost are the proton PDFs without nuclear shadowing. And then the next 3 are the nuclear PDFs, the EPPS 1.3, the EVPS 1.5, and this one is also 1.5. So you see here this point, and now you see they kind of start to drop a little bit below. So this is where you see here. So this is essentially this effect, okay? Now, can you make strong statements or not? To what extent it is modification? I mean, perhaps because these ratios are very flat. So maybe if we were to, make them, so it seems that maybe the data would prefer them to go down steeper, but
that's also in the kind of boundary of the photon flux, right?
Sorry?
Photon flux, because the photon flux also drops.
Yeah,
significantly.
So of course you have also the photon flux is of course here folded in is,
No.
but the EMD also works in the same direction. But it is low PT, so it's maybe not so bad. Anyhow, there are a lot of moving parts here. So, but this effect is there. So you see here, and then again you see the CGC calculation, which is even above this, where it actually should be more suppressed. But that's what it is.
Is that CGC calculated next medium order or just medium order?
Well, this is, I think, I don't remember. Okay, so this is my summary. I guess I'm on time. So we looked at this inclusive charm production at the LHC using FONLL. So we checked these results against HERA. There is relatively okay description, but this large PT is something to be understood. We did these different PDF scale and fragmentation function variations, although I would say that the fragmentation function is still something to be looked at more closely. Now we tested different nuclear PDFs for the UPCs. We included this EMD. The reduction is in this current kinematics by this factor. We do have this, I would say, reasonable agreement with these D0 data. Now, there are some nuclear modifications visible, especially low PT. So it may point to stronger nuclear effects. Now, outlook. So there's a lot of things to be looked at. I would like to look at more at this EMD and fragmentation functions, tests of different nuclear PDFs, and look at this diffractive component as well to have an estimate rather than guess. So that's all. Thank you very much.
Thank you, Anna. Very nice, interesting presentation. Any additional questions?
Well, so you parameterize sort of nuclear effects in terms of PDF modification, but there's another nuclear effect. Imagine you produce photon hits the center of the nucleus, produces a CC bar buried deep in the nucleus. There's energy loss as they try and escape.
Right. Yeah. That exactly. So this is a question about the limits of factorization and universality. That's exactly this, right? And who knows? After there is some effect in terms of this HERA versus UPC, right? The FONLL there seems to be lower. Here it seems a little lower, but maybe not so much. So if you include these effects, do we get the consistency or not? But I do worry about, is the fragmentation the same, and are things like that? How do they affect these things?
People have suggested or considered the photonuclear production J psi threshold to look at a G mu square, the trace anomaly and so on. I wonder if at D0 would any impact, any effect on that along that direction or not.
Yeah,
I just have not the J psi, so probably not just a dipole interaction.
No, that. Yeah, I don't know. I cannot comment on that one.
Okay.
No.
Probably not.
So as an outsider sitting here from the distance, you have this huge uncertainty on the experiment and this huge uncertainty on in your theory. Seems to me everything fits.
You say that reasonable description.
Yeah, but there is except for right. So.
Well, okay.
Yeah,
so this is I've been very generous with this scale uncertainty.
I even take your darker shades, right? All good, right? So my question is, can this be improved eventually, or how?
I'm sure it can be improved.
The data.
So the data can be improved. I think this. on the theory, I think this uncertainty could be improved if, for example, one has next to linear calculation.
Yeah.
That's for sure. So.
And the inner uncertainty of the theory, the dark.
Well, the inner uncertainty is interesting, right? Because if we kind of believe this, now we are starting to, here they have uncertainty,
Yeah.
but now we are moving outside the uncertainty. So what does uncertainty mean? Well, I think there is some, parameterization constraint in these distributions, because, so in other words, there is some uncertainty here, but it's, it's probably like that. Because really these, if we ignore the J psi, right, which we shouldn't, but then, there are no data except for J psi, which if one knows how to fold it in, then it can pin down, and then this measurement can start to
In some sense, you shouldn't trust the uncertainty below 10 to minus 3, right?
Well, even below,
Minus 2 to minus 3.
Yeah.
So that makes your things even wider.
Yeah.
Is that right?
Yeah, well,
But you can turn around and say that the new data would constrain that, right? So,
which is
Of
why
course,
I
yeah.
kept these ones,
Oh,
because
okay.
then I was like, I am not really believing these.
Okay,
too
all right.
much.
Yeah.
Why did you say don't have uncertainty?
Sorry?
Why did you say point don't have uncertainty?
No, because
then you
it's,
should ask Thomas.
you should ask Thomas. But they should have some uncertainty.
Yeah, they should have.
But I don't understand the shape.
Yeah, it's kind of
strange.
Maybe they use the wrong photon flux. That could be.
Could be.
Yeah.
Yeah.
So one thing I meant to ask, this also maybe for Spencer, you guys. So if is there any chance that you have the gamma T? So UPC, you have UPC AA. Can you have UPC AP?
Yeah.
Then that will, when you do the ratio, then that's much
Right.
better, right?
I mean, yeah, if you have PA collisions,
Yeah.
just the numbers are, because of the Z-squared enhancement beats out argon. It's mostly a photon from lead hitting a proton.
And the proton.
And, there is already data public, like J-psi photoproduction.
For JSI, I know.
Yeah,
But
open
for
charm,
this-
it took, I think for all the experiments, it required the run 3 configuration.
Oh,
So
that's right.
there will be a PA run in run 3 or run 4, so I expect we will do that.
That will take care of some of that.
Yeah. So that.
For
and
example,
yeah.
For example, photon flux and found the theoretical uncertainty there.
Right. So you will have different. Yeah. So then you will have this PDF, right? So then we have this PDF, right? And then hopefully in 10 years you have EIC. So then you don't have you have a different photon flux. So hopefully with all
That's true.
4 measurements one can have.
That's a kind of a general comment I always have for this. Although people say Spencer also believe that you could also study already saturation physics in AA and LHC, PA and LHC, Peter would also try to push for that. But all this AA or PA, you have additional uncertainties. So I think EA definitely have much more advantage in terms of interpretation.
Mm-hmm.
Small question from non-expert. So, for example, in this uncertainty, so do you have uncertainty from the fragmentation in it, or
So not necessarily, because this thing here. So the smaller one is in the uncertainty on the initial PDF. The larger one is really the scale uncertainty of the theoretical calculation. So it's there on the charm quark level, right? What is renormalization scale? If you go to sufficiently higher orders, this uncertainty should shrink. But it's still there for at these scales. Now, the fragmentation function uncertainty, this is what I was trying to more or less start to play here, although I didn't exploit it too much, varying these parameters. So this is like one fragmentation, this is another one. This is, you should really look at this blue one, which is sort of consistent, although if you look at so there is that part I haven't explored we haven't explored too much, and this is something that needs to be explored because there is no guarantee that, for example, it's exactly the same fragmentation in UPC on nucleus than on a proton, right? I mean, it's a different environment. So
in HERA data, you showed the PT spectra, right? And then you see some deviation at the high PT.
Yeah, you see some deviation here. I don't really.
But this is not PT, right?
It's not PT, but this is in PT bins, right? So now, of course, I have a PT distribution here. So if for example, here I have the PT spectrum, and this is the FONLL, and this is fixed order, and this is FONLL. However, here it's not directly comparable to what I showed at HERA, because there I did have different parameters for them, and here I have the same. So I'm probably exaggerating this difference here, but here this is really the difference between the fixed order and the FONLL calculation. But the fragmentation, any change in fragmentation also is going to change this spectrum this way, right?
And then I have no idea about the fragmentation, the carbonized fragmentation function, but is it how reliable is it? I mean, I don't know how.
No, I mean, these have been fitted in hadro for heavy quarks for mesons in hadro production. So they are, I would say,
they've at least fitted to something.
Yeah, they're fitted to some data, but there is always a question. You have E plus and minus, you have PP, and then you have EP.
There are some uncertainties.
Yeah, then it's there are, and so this is another moving part here in this puzzle, right?
So my real question, in the model side, we cannot include the CGC and nuclear PDF at the same time, right? You're double counting.
So I'm not doing here the CGC calculation. Now, of course, you could do something maybe halfway, in which you kind of try to model this collinear PDF a la and include some small X effects in that, but also in the end you also have a small X effect in the coefficient function. So whether there is a double counting, I mean, some part, you could argue that there is some, in a sense, this parameterization does take some effects of the CGC. I mean, we just don't know how much, because one thing about the CGC is that potentially it is able to predict you the low X evolution. So once you have this function at some X, the small X evolution should tell you how it evolves down. Whereas here, this is a DGLAP, so essentially you don't have that power. So in that sense, one could argue that one could have some resummed evolution for the collinear PDFs that have small X effects.
Yeah.
But that's.
So the short answer is the double counting.
No. So you cannot put it together.
You cannot put it together. So there will be some double counting, right? You would have to, or in other words, you would have to do a very careful analysis not to have double counting. Let me put it this way. You can put some resummation inside the collinear framework, and you can, yeah, that's.
Okay, so you have.
Yeah, a small question about this plot. This shows up very often. What do I make of the width of those error bars when I go to the lower and lower axis?
So-
Very narrow band.
So honest answer is you should cut this plot here.
To the left. Thank you. No. To the right, right? We keep the right.
Yeah, you keep the
Yeah.
right and you throw the left.
So please,
for those of us-
pass this honest message to many people.
For those of us on Zoom who can't see where you're pointing, where is the limit?
Can you read off the X that you pointed?
So x 10 to minus 2, right?
Few
Right,
times
you
10 to minus 3.
Few 10 to minus 3.
So we shouldn't trust it below a few 10 to the minus 3.
Yeah, that's right.
Interesting.
Thank you. I mean, that's my. I'm
Anyway,
asking this question a million times, and
Yeah.
you're the first person who actually straight up in microseconds answered the question.
Well,
I mean, that's where your data tells you. I mean, you
Well,
don't
we
know
can
that
go
it's,
here.
Yeah.
what data do we have? Now, there are data
Well,
from.
data is one thing, but the reliability of the
Right.
of the extrapolation and the reliability of the error band,
Yeah.
in fact, around it when you extrapolate
Exactly.
is something important.
Yes. So this is to answer this question, this is why the NNPDF, so the EPPS or other, they have what is called the parameterization bias, right? Because they assume parameterization and then you
Yeah,
just
that's right.
go where your curve goes.
Mhm.
But the NNPDF have these more flexible neural network. They allow for more variations. So they should have more. So in principle, they should have essentially wider variation as you go to lower and lower x. But here, in fact, I don't see that so they are still quite, they still have quite a small, I mean, they even have smaller bands than the EPPS, so
Maybe they also have
maybe
some
they
bias.
also have some bias there, and
From an experimentalist point of view, when we argue for experiments that are supposed to measure something very precisely at x to the minus whatever, people see plots. Well, sorry, but your gluon distribution function is known with that precision to 10 to the minus 6.
Yeah.
Why would you ever consider measuring anything? And that's very difficult.
yeah.
That puts us in a difficult situation.
Right.
And it's a comment, not a question.
No, and then you see what happens, right? I mean, right? I mean, we have these error bands, right? And then the experiments start to say, well, that's
We
not
are outside the
outside your error bands,
I mean, you
even
can-
your theory.
You can also turn that around, constrain it. Okay. Okay, let's thank Anna again very much.